hand things over to you, Tina. Thank you.
So I'll share my screen and just let me know. Can you see this? Yep. Yeah. Okay, cool. Yeah, so yeah, as you said, I'm Tina and I'm a PhD student working at the University of Southampton on a project titled Human and Biomechanical Considerations of Hand Joint Disease. So I'm just over 2 years into the PhD today. So I hope to sort of give you some background into the project, but then also talk about the progress we've been making in delivering an engineering project with a large public involvement and engagement focus. So to introduce, we'll start off talking about the hand, which is the main focus. It's one of the most complex structures in the human body, and it can perform countless actions, including those that are crucial to our everyday lives. So in 2013, it was recorded that more than 1.5 million people in the UK sought treatment for hand or wrist osteoarthritis. And this affects joint movement and function, compromising an individual's daily life. So what osteoarthritis is a degenerative joint disease in which can affect any joint in your body, including the hand. And it's categorized by sort of the breakdown of articular cartilage, the remodeling or change of shape of the surrounding bone, but then also the thickening of the joint capsule. So I'm just going to bring out this laser that I hope you can see on the screen. So there are two images on the screen. Hopefully you can see the one on the right is showing sort of a change in shape in the bone compared to the two other bones on the left and right, as well as sort of a thickening of the finger. So you can see the outline here. And what that could indicate, although it's on an X-ray, that the soft tissue sort of structure has changed as well. So whilst hand joint disease has a major impact on people's confidence, independence, and quality of life, so the biomechanical analysis of the hand and wrist joints are at an early level of understanding compared to your lower limb joints, so your hips or your knees. So where does biomechanical engineering come in? Well, it's a field where we combine mechanical engineering principles to biological systems. And what we can do, some of our analysis involves characterizing the bones, the joints, and the muscles to really understand how they work individually, but then how do they work together to move the whole system. And examples of where this can be applied is in orthopedics, prosthetics, orthotics, and what I've mentioned here also, computational medicine. I'll get into the computational medicine stuff later because that's the main focus of my project. But on the right-hand side, there are some examples of finger joint implants. So here we have a metal polyethylene implant, so that's a metal on plastic. And then in the middle, we have a pyrocarbon one. So hopefully on the right-hand side, you can see an X-ray, which shows how the device would actually be implanted in the finger. So what it hopes to do is separate the bone surfaces so they no longer grate on each other, but then also give the patient more mobility and the ability to move their joints as well. So the whole question is, as I said at the beginning, it's an engineering project with a public involvement approach. Here is the engineer, and whilst there's been a real push for involvement of non-researchers in research, biomechanical engineering is largely technology driven, which means that the tools that we might design are designed for those that are living with the condition being treated rather than for them. So what we want to do, you want to do it with them, because whilst it's a field in which is quite multidisciplinary, so we collaborate with health scientists and surgeons, nurses and doctors, we also want to see how involving the public voice could impact our research. So having an approach in which our colleagues in health science do a lot and seeing how that might present itself in an engineering environment. So just to give some background, I did mention computational modeling at the start, or computational medicine. And what that is, it's using computers to sort of simulate and study complex systems. And this is used widely across the biomechanical research field, and it helps us to test certain aspects of a system without actually interfering with a patient's treatment. So it's just, trying to simulate and understand what would be happening in the body before actually like cutting anybody up or trying to understand what's going on the smaller microscopic level. Examples of how it can be used. It can be used to test new joint implants before they're trialed in people, but it can also be used for planning for surgery. So I've taken this from a sort of conference paper by Phillips and al. And this is an example of a computational model of the finger, what they call a force-dependent kinematic model. And what you can see is that it's moving from full extension to flexion. And it doesn't look very much like the finger that you would see in the body, but the sort of lines that you see would represent your ligaments, your tendons, your volar plates. So all of the things that are necessary to produce finger motion have been simulated on the computer, and they can use that to further understand what devices we need to develop or what is actually going on that level. So the actual PhD talked a lot about engineering in general, how we need more PPI, but then also the focus of the project, which is the computational model. So the aim overall is to evaluate how we can incorporate patient and public involvement and engagement, and sort of how that impacts the design, implementation, as well as dissemination of a biomechanical engineering research project. So how we aim to do that is by involving and engaging members of the public to guide the development of this project, to consider how we can relate the sort of engineering technology we have, so the state-of-the-art computational and biomechanical analysis, to the outcomes from the public involvement. And then, of course, using aims 1 and 2 to define sort of guidelines for other engineers so that they can apply it in their own research. So yeah, having it be like a case study as well as an actual engineering project. So where did we start? We started, of course, with public involvement. So here is just an example of one of the Jamboards that we created during the early sessions. And what it shows, hopefully, in that session, we were talking about the impact of hand OA. And we talked about activities of daily living that are affected. So things like cooking and baking, hobbies, so like the smaller movements like sewing and writing, threading, flipping books, like flipping pages in a book, even like IT skills, because one of the things they say is if you can't write, you can type on a computer, but even stuff like that could be difficult with the repetitive motion. So we talked about how you can adapt. So it could be heating the joints, changing the motion, resting in between activities, stuff like this. But we also focused on a really big area, which was joint instability and what that actually looks like from a lived experience perspective. So yeah, this was just a really fun way of getting the public contributors and the engineers in one room and just talking more widely about the lived experience. So from those sessions and the PhD, over time, we formed this team of public contributors, engineers, and health scientists who strongly advocate for this collaborative and co-productive approach in creating research that not only involves the public, but engages them, because they also want to understand research in a way that they can use it, not just a way that we can, publish a paper or generate a code. Like, it has to be something useful. So here are some of the key factors associated with hand OA that we discussed during those early public involvement sessions. So this is just like quite general, but like we said, we talked about joint instability, the impact on activities of daily living. Some interesting things we talked about relating to the computational modeling was the representation of the data, the usefulness of a model, daily considerations. So a big one that I always say that I never knew starting this out was the impact of like diet and weather on hand osteoarthritis and what it's like day to day. Like one day in the cold, it's harder to move, the joints are more stiff. But then there's also impacts when it's really, really hot. So those are the things that, when we're designing a computational model of the finger and we're making all these assumptions, is that in the back of our mind kind of thing? So the big question back then was, how can these insights inform the research? And we've moved on from there to design sort of the outcomes of this PhD project. So of course, we can't address all 9 because of the PhD, there's time constraints and funding and all this jazz at the university. So we thought, what can we address right now? Sort of what can then also be the legacy of the PhD project overall. So we started off with the contributors and we had those consultations. And so we said, okay, 9, we're going to reduce it to 3. And we chose joint instability, patient variability, and hand joint disease awareness in general. So the hand joint disease awareness was that there was sort of a, not a disconnect, but compared to lower limb joints, there's a lot more information out there on your hips and your knees and not so much on your hands. So we thought, how can we use this project to communicate that or address that? Patient variability concern that everybody is different. So if you are going to make a computational model, it being person specific, is that representative? And again, joint instability was something we haven't seen a lot in the literature discussed from a computational model perspective. So I want to show a scary image. It looks scary, but I will talk through it. So we had this first image up there just now, and these dashed lines are to show sort of the approach we've taken at each stage. So I'll start off with the patient variability. So those were the consultations. We had all these discussions about the lived experience. We talked about how it's important to understand that everybody's different, because even within the group of contributors, they all had different experiences. So we thought, we have this data from a previous study, we could create a sort of subject-specific movement model, but instead we thought, let's sort of understand the variation between the data sets that we have. So we created a statistical shape model, which I'll present later on. We also talked about joint instability, and that's something we're working on now. Can we design a study which can help assess the performance of activities of daily living, but how does joint instability impact that? And obviously the general awareness, we've done a public engagement project in which we've tried to engage not only the public, but the university and then a wider group of researchers as well. So hopefully what you can see is that although we started with the consultations, we've kind of branched out, and now it's a lot more co-productive and collaborative. So this project was co-produced, contributors were on the team as sort of the leads. Here, we're currently co-designing that study, what needs to be in it, what sort of outcomes do we want, what is our hypothesis. And then, yeah, for the workshops, we continue to co-deliver those workshops. And hopefully by the end of the PhD, we'll have sort of reflections and recommendations in which we can give other engineers and they can use and sort of see if any of this applies to them and then how they can get started on their own PPI journey. So yeah, we're addressing these 3. So the next slide will just be introducing the progress that we've been doing so far. So I mentioned that we have this computational modeling data. So that was collected by Metcalf and al. Back in 2015, I believe. And the images on the left just show the data collection method. So they got participants, 10 right hands, free from hand or wrist disease or injury, with an average age of 31 years. They CT image those in 3 different positions. So fully flexed, fully extended, partially flexed, and then sort of fully flexed. Then they took the readings, generated 3D meshes, and sort of did their own analysis on that. But how we could use that is by creating what we call a statistical shape model. So that sort of provides an average shape of the population of data sets you have and can give you information on how those data sets vary in structure. So you start off with sort of your images, so your CT images, then you use those images to create 3D shapes. And then from those shapes, you can create an average shape. So you take each one and say, out of all of them, this is what they would look like on average. And then you put it through an algorithm in which will sort of spread out your data, organize it, so it will display how it varies from most variation to least variation. And then you can either do some analysis on that, so get some numbers, or you can visualize how it would differ. So I'll actually show you that for how it applies to my data. But what's really good about this method is that it can help you understand the variation in structure, but it can also help you evaluate treatment design, because as we said, not one size fits all. So you can sort of design something, use this model in one version of variation and see how that might change the performance or anything. It's the same with clinical outcomes. You could take the model, see if that clinical outcome varies with the shape structure changing. But also you can use it to inform sort of diagnosis, treatment, and sort of surgical planning, like we said before. So this is an example of sort of the CT scans that we had on the finger and what we've been able to do recently with that. So we've taken our 10 CT scans, they've created 3D meshes or 3D models of that. And so I've taken it, created a mean shape, which is this pink one. So that's the average shape. So this is the ring finger, the average size of a ring finger. Then by putting it through that program, it's told me this is the smallest and largest size within the population. So the light blue is the largest, and then the dark blue is the smallest. So what this is telling me is that this first variation, so this first mode of variation is size. Within the population, the one thing that varies the most is size. So if we skip to the next one, what they're telling me that the second mode of variation, so the second thing that varies the most within those 10 right hands is the position along this axis. So it's hard to see because the dark blue does take a lot of the color, but it's kind of shifting a little bit to the right. So this light blue is further along than the dark blue. So it's showing that position-wise, that's the biggest variation in second. So what can we do with this? So we have 9 modes of variation, and the examples of what it shows is differences in size, difference in position, but also difference in orientation. And on your left, you can see sort of the size for the 4 fingers. So we have our sort of index, middle, ring, and then our little finger. And it's just an example of how size varies. So this is sort of the small, medium, large kind of thing. So this model has currently been shared on an open source repository, so you can actually access it online. So here's the website. And we encourage the community to basically use it, download it, contribute to it if they have more data sets, sort of share with us how you've used it. This paragraph is just an example, which I loved, from a contributor about the usefulness of this sort of model and how like not only engineers can use it, but surgeons and doctors, and just about how it's important to get something out there first, because there isn't anything out there on an open source repository like this. So to see how, you know, their research might change considering the different types of shapes and sizes out there. We do know that this is a data set which contains information on hands that live free from hand or wrist joint disease. So that's something we are aware of. And so the next step would be everybody in the community sort of band together and understand how we can move further to understand different sort of pathologies of the hand. So that was the computational modeling. So how we're addressing the general awareness is we applied for the Public and Community Engagement Development Fund, and we started the How Would You Handle This project. I didn't come up with the name, I can't claim that. That was my supervisor, Cheryl. So we wanted to develop an educational, but also interactive website to raise awareness of what it was like to live with hand osteoarthritis. Obviously, this is perspective from some people, but it's a start because, again, one of the big things we noticed was that there isn't as much information out there on the hand. So this taken into consideration, we also wanted to use this resource as a way to communicate to researchers why they should be considering these insights and how they design healthcare technologies. So yeah, it was a really fun project, and it sort of helped sort of spearhead more of our dissemination and sharing our work out there. But it's a resource which contains infographics and resources and blogs and our social media campaigns. What's great is that this infographic was designed with student interns. So again, it was a very co-productive project. So we have sort of those 9 boxes you saw earlier, but designed in more of a graphical and inviting, interesting way. So like I said, some of the weather and diet stuff we talked about, the age representation, how, you know, researchers and people designing interventions can actually use it. And just, yeah, we're also always communicating about public involvement. But as well as that, we try to go out to science festivals and sort of talk with members of the public about the research that happens at the university, but also to give the public a better appreciation of what reduced hand function might look like. So again, we try and do it in a fun way, but then hone the message back that public involvement is where this all starts, and this is what it's like to live with this certain condition. So, oh yes, last few slides. So we do engineering seminars at the university. So we thought it's great that we're trying to share this as the PhD about the value of public involvement, but it's important to start early because I first was introduced to PPI in my final year of my undergrad. So we thought, how about we do our own seminars for the younger engineers at the university to talk about not only the value of public involvement and engagement, but then also try and sort of gain an understanding of what the current sort of community know about public involvement and how that could be applied to biomedical engineering. So it's really fun. It's both like a way we can observe them and how they think, then another way that we can sort of open the discussion and learn from each other. So we run, I think we counted 6 of these now, including one at a conference. But one of the activities that we do is design a word cloud. So we get them to answer the question, what might the benefits be in involving patients in the public? And then they include their words, and then we discuss what those words might mean. So this is one from undergraduate students. So, maintaining interest, avoiding agenda. And what's nice is that we ask these questions at the start of the seminar and then again at the end, and we can see how sort of their answers might have changed based on the learnings that have happened during the session. So it's just, yeah, really, really fun. And penultimate slide. So as well as the PhD, the public involvement and engagement, we've also found ways to share it on an academic level as well. So going to conferences, and I could probably say we're all co-authored on the public involvement papers. So we have the first one, which was at a surgeon conference in London last year. And that was just the first one we ever did, was the value of involving members of the public in developing bioengineering technology. Then we did one at the World Congress of Biomechanics. So that was online, but in person in Taipei. And that was sort of sharing those 9 boxes that you saw and how the other biomechanical sort of engineers in that field could sort of take those ideas and create and design their own sort of projects. We also have shared the statistical shape model. That one they're not co-authored, but that was the first one that I put through for the proximal interphalangeal joints, so sort of the first version of the statistical shape model. And then the latest one we've been to was we conducted a workshop at the Biomedical Engineering Conference, and that was on the scope of integrating lived experience insights in the design and implementation of research. So that was more of a formal seminar for the biomedical engineers there. So just to summarize, because I haven't been speaking in a while, so public contributors can be involved in any and every stage of the project. What we find is that biomechanical engineering research is quite technology driven. So there is scope to include more public involvement and engagement activities in the research process. The next steps for the PhD is co-designing a biomechanical assessment study to sort of evaluate the impact on joint instability on hand function. So thank you so much for listening. And here is my email or my Twitter. And yeah, special thanks to the funding bodies, but then also my contributors, my supervisors, everybody else that supported the project so far.
Thank you.